Welcome back to the Network Architecture Design Series. I'm Ray. In this episode, we're going to examine a common problem. Why does Microsoft Teams break during all-hands meetings? Engineers often assume it is a firewall problem. However, as we will discover, the firewall is only where the symptoms appear. The actual root cause lies in the network architecture itself. We previously covered this issue in the episode 1. Let's start by reviewing it. Here is a traditional enterprise network from real world. This network consists of a headquarters in New York, 3 data centers located in New Jersey, New York, and Dallas, along with many branch offices. All of the company's internet traffic is routed through its New York headquarters. This is a typical design for traditional enterprise networks. This company uses Microsoft Teams for meetings. Microsoft Teams is a cloud service. It's outside the company's infrastructure. It is accessed through the internet connection at the New York headquarters. When Microsoft Teams is used for small group meetings, it works well, no noticeable issues. However, during company-wide all-hands meetings, audio and video performance quickly degrade. MS Teams becomes unusable. After extensive testing, engineers noticed that the firewall leads traffic congested, packet loss, latency, and jitter. The firewall appears to have become a bottleneck for handling the massive volume of MS Teams traffic. But here is what made this problem difficult to diagnose. Engineers attempted to bypass the firewall completely, but the problem has not yet been fully resolved. Let's dive into this problem. Traditional troubleshooting focuses on links, devices, and configurations. But what if the root cause lies outside this scope? What if the problem actually is from the network design? In that case, no matter how much troubleshooting you perform, you will never be able to resolve the issue because you are looking in the wrong direction. Therefore, we need architectural thinking. We must consider the network architecture itself. Traditional engineers usually focus on the question, how? How to fix it? How to configure it? How to test it? Architects usually focus on the questions, what and why? For example, what does it actually mean when Microsoft Teams is breaking? Why is it happening? Once we understand the what and the why, the how becomes much easier. Users from different branch offices reported that Microsoft Teams failed during large-scale all-hands meetings. It includes audio cuts out, video freezes, people are dropped from the meeting. But when MS Teams is used for small group meetings, it works very well. From network engineers' perspective, voice and video are experiencing performance issues. It means packet loss, latency, and jitter. It is important to note that here the what is not merely a description of a problem or symptom. We translate it into the language of network traffic and packets. For example, when users say that Microsoft Teams is breaking, we translate that observation into network behavior, packet loss, latency, and jitter. Only after clearly defining the what can we begin asking the why. Regarding root cause analysis, RCA, we start with the effect we observed and trace it back to its cause. Here, effect is MS Teams breaking during all-hands meetings. From a network perspective, it means packet loss, delay, and jitter. Now, let's ask, why do packet loss, latency, and jitter occur? The answer is because data packets are encountering congestion somewhere along the path. Engineers typically use tools provided by Microsoft, such as the Microsoft 365 Network Connectivity Test, to measure packet loss, latency, and jitter between the user's location and the Microsoft network. At the Internet Firewall, engineers observed high CPU utilization, interface congestion, packet drops, and increased latency. So, the firewall appears to be the problem. The engineer attempted to completely bypass the firewall. The symptoms improve somewhat, but the problem does not completely disappear. This tells us something important. The firewall may be a bottleneck, but it is probably not the root cause. So we continue asking why. Why is so much traffic arriving at the firewall? The answer is because the large-scale all-hands meetings generate a massive amount of Microsoft Teams traffic. But that leads to another question. Why does all of this traffic arrive at the headquarters firewall? The answer lies in the network architecture. The company uses a centralized internet breakout design. All branch internet traffic is routed through headquarters before reaching the internet. It is worth noting that the centralized headquarters internet breakout is a common best practice design in traditional enterprise networks. You might be wondering, what is the best practice design in traditional enterprise networks? Let me briefly introduce it here. Traditionally, the best practice design for enterprise networks is something like this. All branches connect to headquarters. Headquarters connects to all data centers, all branches, and internet breakout. In this architecture, the headquarters acts as the regional hub. All user traffic is hairpinned through headquarters, and through headquarters, users can access any data center, the internet and cloud services, and talk to other users. This architecture is excellent in security control, compliance, and operational simplicity, but it's poor in SaaS performance and WAN efficiency. It provides moderate scalability and user experience. As we discussed earlier, when large-scale all-hands meetings generated massive traffic, traffic from the entire company converged on the headquarters firewall, causing it to become a bottleneck, ultimately causing Microsoft Teams to fail. Why does MS Teams break during all-hands meeting? In our earlier root cause analysis, RCA, we started with the effect and worked backward to identify the root cause. In this section, we take the opposite approach. We start with the root cause and follow its consequences step by step. By doing so, we validate the conclusions of our RCA and deliver a clear summary. Let's start with the full chain at a glance. This architecture routes all internet traffic to headquarters. Furthermore, large-scale, company-wide MS meetings generated massive amounts of traffic, causing a surge of traffic to hit the firewall, which, in turn, caused the firewall to become congested and act as a bottleneck, triggering packet loss, latency, and jitter, and ultimately leading to MS Teams malfunctions. Now that we understand the root cause, the solution becomes clear. We have two options. Option 1. Upgrade the firewall and the internet bandwidth. Option 2. Allow local internet breakout. Let's start with Option 1. Option 1. We upgrade the firewall and the internet bandwidth at headquarters. In network scalability strategies, this approach is called scale up. It may provide temporary relief, but it does not fundamentally solve the problem. As the company grows, or as meeting frequency increases, you will hit the ceiling again. The bottleneck moves. It does not disappear. Let's take a look at Option 2. Option 2. Allow local internet breakout. Instead of forcing Teams traffic through headquarters, Option 2 means that we allow every branch to access the internet directly and reach Microsoft Teams without the unnecessary detour. In network scalability strategies, this approach is called scale out. This is an architectural solution. Traffic is distributed across many sites. The headquarters bottleneck disappears. It is worth noting that distributed internet breakout is a common best practice design in modern enterprise networks, which leads us to the next question. What is the best practice design for modern enterprise networks? Let me briefly introduce it here. Modern enterprise networks should be designed around cloud applications. Applications such as Microsoft Teams, Microsoft 365, Zoom, WebEx, and Salesforce are cloud applications. They are hosted in the cloud and accessed over the internet. Therefore, modern network architectures aim to bring users closer to cloud applications. Instead of the traditional centralized internet access through headquarters, modern designs distribute internet access closer to users, at the branch level. Let's look at how modern enterprise networks are actually built. SD-WAN is commonly used in modern enterprise WAN architectures. MPLS and Internet circuits serve as the underlay transport. User traffic is carried across overlay virtual networks, which can be designed with great flexibility. With SD-WAN overlay networks, different user groups and application types are placed into different segments. For example, we can segment employees, guests, IoT devices, compliance traffic, vendors, and cloud SaaS applications. Based on different traffic patterns, we construct their respective overlay networks. For user-to-user communication, we make all branches connect to headquarters over their respective segments. Through headquarters, users can communicate with each other. For user-to-data center communication, we make all branches connect directly to data centers over their respective segments. For guest internet, IoT, and employee cloud SaaS traffic, we take advantage of the SD-WAN Direct Internet Access feature, enable it at the branches, and allow guest internet, IoT, and employee cloud traffic to egress directly through local DIA circuits. For security, organizations have two main options. We either use the built-in security capabilities of SD-WAN edge devices or deploy cloud-delivered security platforms such as Cisco Umbrella or Zscaler. Either way, security policy is enforced at the local breakout point. Traffic no longer needs to backhaul to headquarters to pass through the central internet firewall. As a result, network congestion decreases, WAN traffic is reduced, packet loss decreases, latency decreases, jitter decreases. Most importantly, the MS Teams problem we started with, it disappears. Not because we fixed the firewall, but because we fixed the design. In this episode, we shifted our mindset from traditional troubleshooting to architectural thinking. This means we focus on architecture design and on the questions of what and why. Through this approach, we identified the true root cause behind the Microsoft Teams failures. Starting with the next episode, we will begin a new section of this series, the Art of Tradeoffs. Every architectural solution involves a trade-off. Local internet breakout solves the Teams problem, but it introduces new decisions around security, visibility, and control. That is exactly what we will explore next. This is one of the most important topics in network architecture, and one that is often overlooked. If you have any questions about this case study, please leave them in the comments below. And if you found this video helpful, don't forget to like, subscribe, and follow the series. Thank you for watching. I'm Ray, and I'll see you in the next video.